Hello everyone, and a very good day to all of you who are watching this video. Today, we'll be talking about matrix operations to solve linear equations or sets of linear equations. We are Group 6, and we have named ourselves the Matrix Maniacs, and we have enrolled in Engineering Mathematics 1 course, and our lecturer is Dr. Ang Tao Keong, and we want to thank him to give us the opportunity to talk about this and do this creative work. So, first of all, let me introduce my team. So, I'm the team leader, I'm Jawad, and I'm followed by Thamid, Tanhim, Sajid, and Pasha. So, today we'll be talking about system of linear equations, which is a concept in the huge tree of mathematics. You can call this a leaf, and we have two subtopics to talk about. One is elementary operations and the other is inverse matrix method. Both of these have two other subtopics. So for elementary operations, we have the Gauss and Gauss-Jordan elimination method. And for the inverse matrix, we have inverse matrix itself, which contains the adjoint method and also the Cramer's rule. So to speak briefly about all these methods, I want to start with elementary operations. These are like specific and fundamental operations performed on the rows of a matrix that preserve the solutions of the associated system of linear equations. ERO ensures that the final solution that we are supposed to obtain from the matrix doesn't get affected by the modifications that are made. So while performing ERO or any method that follows the rules of ERO, you can be assured that no matter how much modification you apply to your matrix, it'll stay the same and your answer won't be affected in the end. Next up is Cramer's rule, which is the simplest method among all the methods that we're going to talk about today. So this is for solving systems of linear equations using determinants to be specific. It provides a formula to find the unique solution for each variable in a system by expressing it as a ratio of determinants. Um, and the other method here is inverse matrix. So I want you to consider a system of linear equations represented in matrix forms such as Ax equals to b, which is the most common one, where A is the coefficient matrix, x is the column vector of variables, and b is the column vector of constants. By calculating the inverse of the coefficient matrix A and multiplying it by the column vector of constants B, we contain the column vector x, which represents the solution to the system of linear equations. However, it's important to note that not all matrices have an inverse. For a matrix to have an inverse, we all know it must be a square matrix and have a non-zero determinant. If the determinant of A is 0 or A is not a square matrix, the system of equations either has no solution or has infinite solutions. Next up is elementary operations, and I want to give a brief description about what Gaussian elimination and Gauss-Jordan elimination is. So to start with, Gaussian elimination is also known as Gauss elimination method. It's an algorithm used to solve systems of linear equation. It systematically reduces a system of equations into an equivalent triangular form, making it easier to solve. For Gauss-Jordan elimination, it continues the row operations to ensure that all entries above and below each pivot or leading number equals to zero, resulting in a more reduced form. Once the reduced row echelon form is obtained, back substitution is not required in the Gauss-Jordan method because all variables are already solved for. And now I'm going to pass the mic to my fellow teammate Hamid to discuss the conditions that are required for these methods to work and also provide an explanation and a demonstration of how these methods are used to solve problems. And thank you for listening.
Hello everyone, I am Mohammad Hamid Rashid, and today I will be talking about the conditions for the system of linear expressions. At first, for non-homogeneous system, we will consider the rank of the matrices with the coefficient of the variables x, y, and z as PA, and the rank of the augmented matrix found by the system of linear equation as PAB. And when the rank of both these matrices is equal to the number of the variables, then the system will have a unique solution. Again, when the rank of the matrices of the coefficient and the augmented matrix is equal, but it is less than the number of variables in the solution, then there will be many solutions. Again, when the rank of the matrices of the matrix with the coefficient is less than the rank of the augmented matrix, then the system will have no solution. In case of homogeneous system, when the rank of the matrix with the coefficient is equal to the number of variables, this system will have trivial solution. Again, rank of when the rank of the matrix with the coefficient is less than the number of variables, then the system will have many solutions. Now we will see a demonstration video containing an example solving the system of linear equations. Here we have the system of linear equations, and we will solve it using Gauss elimination method. At first, we are going to form the augmented matrix of the system by using the coefficient of x, y, z and the constant. And then we would need to perform elementary row operation, also known as ERO, to obtain the REM form of the augmented matrix. Over here, we are gonna need to create leading one of each row. So we would need to do different operations such as B2 minus 4B1, which is subtracting the second row by the 4 times of the first row, which would give us our first element of the second row as 0, and then we will obtain the second element as 1, which would be the leading one. And following the rules of REM, we would get the leading one and form an REM matrix in this form. After that, we're over here we can see the rank of the augmented matrix and the rank of the coefficient matrix is equal to, both of them are equal to 3, and also the number of variables x, y, z is 3. So we can substitute the coefficient of the of x, y, z as following the augmented matrix, and we can form three equations over here. And by substituting the value of z, we can obtain the value of y, and substituting the value of y and z, we can find the value of x from. And we can see we will find the solution as x is equals to 5, y is equals to 4, like this, and z is equals to 2. Now we're gonna solve the same system of linear equations by using the Gauss-Jordan elimination method. This method is more or less like the Gauss elimination method, except we need to perform ERO on the augmented matrix until we achieve the RREM of the augmented matrix. Here the RERO of the matrix is will be the same as the previous example, since the the system of linear equations for the previous one and this one. This example is the same. So after forming the augmented matrix, we have performed the same ERO as before and achieved the REM form of the augmented matrix. After that, we're gonna still continue doing ERO in order to achieve the RREM, or the reduced row echelon form, in order to in order to solve the system of linear equation using the Gauss-Jordan elimination method. After achieving the RREM, we can substitute it into the equation of the system of linear equation, and we won't get three equations as in the previous example. We will directly get the values of x, y, and z from the matrix. Now we're gonna solve a new set of linear equation using inverse matrix method. In this method, we will need to first create matrices of the system of linear equations. First, with the matrix A, which is the matrix formed by the coefficient of x1, x2, and x3, and then is the matrix X, which contains the variables, and the matrix B, which contains the constant. Over here, we can write Ax is equals to B in order to achieve the system of linear equations as in the question. Now by now here we know that x would be equals to A inverse B, which is the inverse matrix of A multiplied by the matrix B. So we would need to find the inverse matrix of A. Where here we are finding the inverse matrix of A using the ERO method. We have two methods to find the inverse matrix. The one of them is using the adjacent of A, and other one is this method, which is using the ERO method. And finally we would have achieved the A inverse matrix. After finding the matrix, in order to find X, we need to multiply the inverse matrix with B. Here, over here, after multiplying the inverse matrix with the matrix B, we would find a new matrix of 22, 3, and 4. And we know that the X matrix is equals to x1, x2, and x3. From this we can know that x1 would be equal to -2, x2 will be equal to 3, and x3 would be equal to 4, which is the solution of the system of the linear equations. Now we are going to solve the a new set of linear equations by using the Cramer's rule, which, as my team leader has mentioned, is the easiest one of them. As the previous example, we will need to find the matrix form of the linear equation and let the coefficient of the x1, x2, and x3 matrix b is equals to A, and the b is equal constant b, the matrix B. Over here we have achieved the matrix and named it as A, B, and X. Now, in order to solve this linear equation using Cramer's rule, we would need to find the determinant of A, and after calculation, we have known that the determinant of A would be equals to -2. Now, in order to find now, we need to find the determinant of A2. So we need to find also saying the matrix A1. Sorry, A1, as I have said. In order to find A1, we would need to substitute the first column of the matrix A, which is -2, 1, and -2, with the constant with the constant matrix, that is the matrix B, which would be equals to 1, 4, and negative 3. And after substitution, we would have achieved the matrix A1. Over here you can see the first column, sorry, is changed to the B matrix, and the rest two columns are remaining the same. And after that we have found the determinant of A1 as negative 4. In the same process, we can achieve the A2 matrix, which would be by substituting the second row of the A matrix with the constant matrix B, which would be 3, 2, and negative 1 substituted by 1, 4, and negative 3, and we will find the determinant then of A2 matrix, which would be equal to 6, negative 6. And in the similar way, we would need to find A3 by substituting the third column with the constant matrix and find its determinant as well, which would be equals to negative 8. As you can see over here, the determinant. And after finding the determinant of A1, A2, and A3, we would need to find, in order to find the values of x1, x2, and x3, we would need to follow the Cramer's rule, which is x1 is equals to the determinant of a1. Over here, the determinant of a1, which is equals to negative 4. Also, the the determinant of a1 divided by the determinant of a, and for x2, the determinant of a2 divided by the determinant of a. Again, the determinant for x3, the determinant of a3 divided by the determinant of a. And in such way we would have found the value of x1, x2, and x3 as 2, 3, and 4. If we substitute the value of x1, x2, and x3 in the system of linear equation, we would find that the system of the linear equation becomes true. So as a result, we can check for the value of x1, x2, and x3 and find that the value of x1, x2, and x3 is correct. In these processes, we would uh, So we already have discussed solving a set of linear equation using Cramer's rule, using the inverse matrix method, using the REM, which contains two of them, the Gauss elimination method and the Gauss-Jordan elimination method. Alright, that's it from me and for the demonstration video. Right now, I will pass the mic to our team leader in order to give our conclusion.
Thanks, Damit, for your explanation, and I hope everyone understood the concepts of how to use metrics to solve linear equations. To conclude, I would like ask myself, and I think many of you are asking yourselves that why do we use metrics to solve linear equations? I would say metrics provide an efficient and compact representation for solving systems of linear equations due to several reasons. Firstly, matrix allows us to represent a system of linear equations concisely. Instead of writing each equation separately, we can express the entire system in matrix form using the coefficient matrix and the constants vector. This compact representation simplifies the overall notation and makes it easier to work with the equations. Moreover, metrics facilitate mathematical operations such as addition, subtraction, multiplication, and division. By performing these operations on metrics, we can apply various techniques and algorithms to solve the system of equations efficiently. Matrix operations can be computationally optimized, which can lead to faster computations. Moreover, metrics enable systematic manipulation of equations through elementary operations. These operations, as discussed earlier, allow us to transform the matrix into a more structured form, such as row echelon form or reduced row echelon form, making it easier to solve the system. The matrix structure provides a clear roadmap for solving the equation step by step. In addition, matrices are integral to many numerical techniques used for solving systems of linear equations. Methods like Gaussian elimination, Gauss-Jordan elimination, etc. These techniques exploit the inherent mathematical properties of matrices to efficiently compute solutions. When dealing with large systems of linear equations, the use of matrices can significantly improve computational efficiency. Instead of solving equations one by one, matrix-based algorithms can exploit parallelism and optimize computations by utilizing efficient linear algebra libraries and algorithms. Overall, I think metrics provide a powerful framework for solving systems of linear equations by leveraging their mathematical properties, efficient representations, and the availability of specialized algorithms. They allow for systematic manipulation, complex representation, and efficient computations, making them a preferred approach for solving linear systems in many practical applications. That's it from me and my team. I would also encourage you to ask us any question that you have so that we can address it and then solve it if it's possible for us. So that's it from the Matrix Maniacs, and thank you for being with us during this whole time. Catch you guys in the next one. Peace.